Okay, so last time, oh, I suppose I should show you the screen. Last time. Perfect. Okay, last time, of course, we were talking about the ordered list. And if we wanted to add something to this list, the rule is the place that it has to go needs to preserve the order, the fact that this list is ordered, basically. So 58 should obviously go there. Why? Well, because 58 comes after 51, but before 67. Now we could think for a moment, what would like the algorithm be for this? I guess let's say I have 58, and I don't know where it goes yet. I'm going to go back a slide, or a slide before the animation or whatever. 58. Maybe I could ask this question: is 58 less than 16?
No.
No? Okay, all right. Let's go to the next one. Is 58 less than 23? No. I mean, if it's not less than 23, what must that therefore mean? It's greater than or at least equal to, right? Okay. So if it's not less than 23, it must be greater than or equal to 23. So is it less than 29?
No.
No. Less than 40?
No.
Less than 51?
No.
Which of course means that if it's not less than 51, it must therefore be what? Greater than or equal to 51. Okay. Is it less than 67?
Yes.
Okay, perfect. Because a moment ago we just concluded that 58 must be greater than or equal to 51. But we also just found out that it's less than 67. And that must therefore mean 58 goes where? Between the two. Let's say I was doing this operation. What's the computational complexity of this one? N. Why? I heard, but I'm pretty sure you know why. So that's good. I heard a mumble from the crowd, but yeah.
With a list, could you use like an implementation, like when you're trying to figure out where it would go, right? It would be on the order of n because you're going for linear.
Yeah, the way we're doing like the linear search through. Yeah.
So could you implement it with a map to make it so it would be on the order of 1? Because then you'd be able to find immediately which ones would be like where it would go.
But how would you? I'm not sure what you mean. I mean, I've got my map. I want to add something to it. I don't know. Well, how do I add that to the map?
But good question.
Oh, okay.
Well, I don't know where
All right. So there's only really one way to add something to this list, because the rule of the ordered list is that the thing must be maintained in order. So could I tell this ordered list, here, add this thing to the front? No. I mean, maybe only if it would belong there. Or add this thing to the end, or add this thing to an arbitrary position. No. We need to add it where it belongs to preserve the property of the fact that this is an ordered list. So we add something, it must go where it belongs. It has to. That's the rule of the ordered list. If you don't follow that rule, then it's not an ordered list, which is fine if you don't want an ordered list. But if you want an ordered list, we need to make sure it's an ordered list. So we can't specify where we add it. Can't just add it to the end, front, whatever. So should there be any rules restricting how we remove anything? Any thoughts? I'm seeing a lot of no. I mean, I suppose the only rule is that the list maintains its order. So I think we're okay, because I mean, if you've got an ordered list and you remove something, will that list stay in order? I'm having a hard time thinking of a case where it wouldn't, right? Okay. And remember, is a list of size 1 sorted?
Yes.
Who said no? Someone said no. Let me put it this way. Is there anything out of order in a list of size 1? Is there anything out of order in a list of size 0?
No.
Well, I mean, that's interesting, right? More on that later. Like weeks later. Yeah, so we can remove whatever. Unordered list. So an unordered list is where the order of the elements, it doesn't really depend on anything. We can just add things, whatever. An unordered list is a list where the order of elements is not really based on anything other than the order that the programmer makes. It's just a collection of things. It's a list, and we're putting stuff in it. Cool. So if that's the case, here's my list. If I want to add something there, cool. If I want to add something there, all right. How about there? Sure. It really doesn't matter. The rules for adding to an unordered list, whatever really. We can put it wherever we want. But an ordered list, it matters. With the ordered list, it has to be in the place that preserves the fact that that list is ordered. But the unordered list, we can put whatever we want. How about removing? So, okay, should there be any rules restricting how we add? How about removing? Probably we can do whatever we want, I guess. It's just some collection of stuff. Okay. And an index list. Now this is going to be what you're familiar with in Python. The lists that you've been using in Python are a special type of list, an index list. This is a list where the elements can be referenced by an index, kind of like an array. But it's more general than an array. Because it's an array that can grow like arbitrarily large and whatnot. So the numeric position is called the index, big surprise. It's just like an array. Element position is important. So the fact that something is in index 0 and index 1, it's important. I mean, it's not important for an ordering, but it's important that like that it stays where it was. And it's like the programmer defines the ordering. Every time the list is updated, the indices of the elements will be updated. Meaning, if I've got an array of size, or pardon me, an index list size 5, and I want to add something to the middle, I'm going to have to do, something's going to have to happen, right? I'm going to have to like move stuff, be able to put it in there. We're going to have to, now, after we add another thing, we're going to have another index. So that stuff's going to have to update too. So if we've got this, and I add something to the front there, front, of course, is going to have to be updated. I mean, this is assuming, I mean, the way it's written here, I guess it looks like it's in a linked structure building this list. But we could have an array, I guess. So if we add something to the front there, well, we're going to have to kind of update all the indices, right? Add something in the middle, well, we're going to have to update like half the indices. Add something at the end, well, I guess we just add the fact that there's another index at the end. But the point is, there's a little bit of bookkeeping, I guess. There we go, that's what would happen after. Cool. So, there are some operations that all the lists are going to have. Like removing elements. All the lists we can remove stuff from. We can add stuff to them, but remember, there is going to be a difference in how we're adding things, depending on the type of list they are. So all lists, we should be able to add something to them, but how we do that will depend on the type of list. So those implementation details will matter. Get the size, see if it's empty. So we got maybe like remove first, remove last, remove a particular element from the list. I guess we'll have to like identify it in some way. First, last. First and last, I guess, are kind of like the first and like peak. Remember? It's like look at it but don't remove it from the list. See if it contains something. That might be handy, right? Imagine if I have a list. And the question is, does this list contain a given element? Maybe it'll just return true or false. Seems like a reasonable thing we might want, right? Why not? I mean, we can add whatever we want, really. See if it's empty, get its size, cool. But ordered list stuff is going to be basically exactly the same. The ordered list is going to do all the stuff the list had, but the add is going to be a little different. So we're adding to it. We're adding the fact that, well, we can add stuff to this ordered list this way. Is inheritance kind of on anyone's mind? Yeah?
If you were like inheriting stuff from a certain like parent class that you didn't want people to be able to do in like child class, would you actually be able to say in the child class like restrict that, like you can't do that
Well,
with these?
why would like so?
If you were say like it was an ordered list, could you call something to add from?
Well, no, because there is no such thing as add to front in the base class.
Okay.
But we'll add to front, add to rear, add after to an unordered list. So here, add to front just adds something to the front, add to rear, same thing for after. So we're being very careful with our hierarchy to make sure we don't run into that issue. And add after, well, that's adding an element after a particular element in the list. So I guess, let's say I have a list of like human objects. I would say, okay, I want to add after you. So I'll be like, okay, no, okay, you. So I need to insert something here. Right? That assumes that that thing exists in the list, but anyways. And an index list, add an element at a particular index, set an element at a particular index, so I guess we can like change something, that's cool. Get, index of, remove, all these types of things. Remove something at a given index. So these are things we can do with lists. But we saw 3 different types of lists. So we have lists, which is the high level idea. But then we have 3 specific types of lists. Ordered, unordered, and indexed. But at any point, have we actually talked about the implementation of any of this stuff? No. So it's still all fairly abstract. When we talk about ordered, unordered, and indexed, we still have, like we know how we would use them. We know how to interact with them. So much so that everyone that came from 161, you used lists, right? You used them. Do you have any idea how it was implemented? No. That didn't matter because you can still use it. Same idea here so far. So we can talk about implementations. So given that there's lots of commonality between these lists, let's use inheritance. So we can implement an array list. What other type of list might you want to make? A linked list, yeah. Where that one, the container's not going to be an array. I guess the container's going to have to be a series of linked nodes. Anything we do here with like the array list, we could implement the same ideas in a different way, but we could solve that problem with a completely different container. Pretty neat. So here's an array list. I guess this is a very generic idea of the list. It's just a list. It's not an ordered list. It's not an array list. It's just the list. Array list, pardon me. Ordered list, unordered list, index list. It is an array list. So this array list, what do we have? Well, we've got some sort of list, which is a pointer to the array, which is pointer, well, in this case, it's pointers to squares, but of course, the contents of array, we're probably going to want to have them to be generic. And it knows where the rear is, I guess. Front's always going to be 0, I suppose. Here's the beginning of the header. Default capacity. Ooh, now we've added all this protected stuff. Interesting. Who remembers why I like protected?
Within package or
Sorry?
within package or something you can.
Yeah, it has something to do with package. Basically, it's a way of saying I can access the stuff in the child classes. I can access the protected stuff in the child classes from the parent class, but it's still kind of private. There's still some sort of restrictions. Let's not worry too much about that. Just it's a handy little thing we'll use right now. So the protected things, size, capacity, a pointer to things of type T. Remember, the fact that it's a T pointer, that's just for the fact that list underscore list is going to be an array. It's a pointer to like an array of things of type T. T itself might be something that's of type pointer, but T could be anything. Expand capacity, shift down, shift up, find. You get shift down, shift up. Those might come in handy, we'll see. Find. So see if a given element is in the list. Does this thing exist? Cool. Then what are our public things? Well, we've got our constructors. Remove first, remove last, remove first, last, contains, is empty, and size. Okie dokie. Any questions about what we see? Is there any add yet? So here's wondering, how the heck do I add anything to this array list? One person's wondering, 2 people wondering, you're 3, 3.5, 2.5? Yeah, you wonder, okay. Well, at this point, I mean, an array list, we never really even talked about how we might add something to an array list. But we talked about how we might add something to an ordered list or an index list and whatnot. So I guess the way we've defined it so far, there's no such thing as adding to a basic low level, high level array list. But more on that in one moment. We'll look at specific ideas shortly. But what do we have? Okay, array list. Cool. There's our constructor. Look good? Any questions? Shouldn't look too crazy. It's going to be very similar to our stack, array stack, and our array queue. Copy constructor, same thing. Going to look very similar to those two. Delete, I guess just delete that array called list. Remember, we don't need to delete the contents, the things inside that array, because that shouldn't be the list's problem. Someone else created that stuff that they then added to me. It's then someone else's issue to delete that, to manage that memory. For me, all I need to worry about is the fact that I, the array list, created an array object, an array, and I have to delete it. Span capacity, nothing crazy. Right, looks very similar to every span capacity we've seen so far. Shift down. Have a look at this code. What do you think it's doing?
Bring up the things down.
How'd you know? It's shifting the things down. I guess it was a good function name. Shift down, what's it doing? It's shifting everything down. It gets a starting index. So if I've got some starting index, it says, take this index and copy everything down this way until we're done. And of course, we only have to go to size -1.
Because the size,
Why?
size will be reduced by 1.
Well, size will be reduced by 1. That's also true. But if we don't reduce it by, like, we don't go to size -1, we're going to have an issue where we're going to be accessing I plus 1, which that's not actually in our array. Yeah?
Wouldn't you run into a problem here where if you had, say, index 5 and then you move that thing to index 6, then what would happen to the thing that's already at index 6 when you go to move that down?
Well, in this case, we're only moving something from index 6 to index 5.
Oh, it's going the other way.
Yeah.
So then in the other one where you're shifting the other way, what would happen when you run into that problem?
Well, again, if you were to just call this function, it would overwrite whatever's in there. So if we wanted to make sure we weren't overwriting whatever in there, we're going to have to make sure we get our hands on that first. So if it's a pointer, we're going to need a pointer to that thing before we overwrite the pointer inside the array. If it's just some primitive type or something, we're just going to have to create a variable that holds on to that value, and then we can override it. Let's not worry too much until we see how this is used. Shift up. How's this look? What's going on here? The other way. Start at the end and move everything down the other way. It's kind of to make room in the array. So before, we had the array, we removed something, we had to move everything down to kind of like, you know, make sure everything was a contiguous chunk. Now it looks like this one's doing the opposite. It's taking this and it's finding a spot and kind of going to make room to add something, I guess. Presumably to add something. Pay special attention to the for loop. It starts at size. That makes sense, right? Because size should be the next available spot. I guess after this was called, we might have to update size as well. Find. What's this doing?
We are checking that element is
What do I call this? Everyone should have this answer immediately.
So get
search.
What kind of search? Everybody say the word I'm looking for. Linear search. Well done. Good. So if this is on the final, you'll get it right, right? Everybody say right. Good. Remove first. I guess it checks if it's empty. Otherwise, we remove the element, or sorry, we get our hands on the element, which is what you were asking about. So we get element, which is the thing in location 0. Shift everything down, so we obliterate whatever is in location 0, but that's okay because element is holding on to that thing. We have to decrease size, of course, and then we return the element. Any questions about that? I know a lot of people were commenting that, you know, they're in lecture and everything makes sense, but since they have to sit down and start coding stuff, you know, they get a little worked up, they have a hard time. One, you're normal. Remember, it's weird to be able to sit down and just start coding and get the answer. That's not going to happen. That is not how it works, and if you're expecting it to work that way, you're going to have a really, really, really bad time being a computer scientist. Most of your life is going to be fixing all the errors and figuring out how to write what you want to write. Most of my time is spent debugging. Computer science really could be called like debugging. Because you do that a lot, and that's normal. So, and also, and I know I say it a lot if I sound like a broken record, chances are you're thinking too much. Slow it down, take it easy. What are the simple steps? Oh, well, okay, our exception. Get the element, shift everything down, decrease size, return it. Just, you need to be able to think about these things in their basic steps. A lot of people, they're struggling because they try to think about too much at once. Just take it easy, slow down. Oh, do I need to dereference? Take your time. What is it? Is it a pointer? Do you need the value? Well, then you need to dereference. You know, just take it easy. You know all the rules. You're getting tripped up because you're trying to do too much at once. Slow it down. Yeah.
I have a question about the shift up and shift down. If you had like a full list, and you're like shifting up, how would you not be like overriding the spot prior to it? Like if you had something in index 5 and 6, and you shifted up to like the thing in 6 to 5, how would it not like override 5?
Well, because it actually starts here. And it goes from here to here, then it goes here to here, then here to here. So shifting down is fine because we want to overwrite this. So this goes here. But then your concern is, well, what happens like if we shift this here? Let me draw. Do any of these work? Hey. Find A, B, C, and D, right? If I'm shifting down, and I wanted to get rid of this, well, that's fine, because I say C, put whatever's in here in here. So that becomes C. And then put whatever's in here, D. And then we decrease size. I realize D stays there, but as far as the list concerned, this isn't actually in the list anymore. Remember? The list is the size. In this case, the size, this is going to be the next available spot. So size will be 0, 1, 2, 3. So although there's 2 D's in there, that second D doesn't really matter. Because when I add a new thing, it's just going to overwrite this. So it's fine. So moving this way is fine. Now your question is,
So it got rid of B though.
but that's fine because we got element first. Element is going to be list allocate. So remember, this is remove first.
I was just more concerned about like shifting down without like erasing anything that's already in there.
Well, in this case, we wanted to erase it.
Okay.
So we wanted to remove that thing from the list. So we got it, we held on to it with element. So your element, okay, remember B. And then I override it, and then I'm like, okay, return you. What are you? B. So we're good. Now if we have an issue with shifting up, let's think about how if we were to shift up starting here. If I were to say this thing equals this thing, this would become B. And then I move down and I say, okay, this thing equals this thing. This becomes B. Does that look like what we wanted? Absolutely not. That's horrible. We're going to want to start here. And we might need to expand capacity. But we're going to start here. And we're going to say, this thing go here. This thing go here. This thing go here. And so on. And now this spot is empty, but we'll just overwrite whatever in there. This is assuming we're adding to the middle or something. Did that help anybody? Yeah? No? Cool. Remove last, well that one's easy. we don't have to shift anything anymore. If we're removing the last thing, all we have to do is just update where the end is. Cool. A general purpose remove. Okay, so this looks like it's removing data. So it's removing the thing that has data in it. Now you might be saying, well, if I have the thing I want to remove, why am I looking for it and you want to remove it? You already have it. Well, sometimes we want to have like some values in that list to keep track of something. Like in here, I might be saying, okay, go through and remove the C. All right, cool. That's all we want to do here. So I check, is it empty? No. So find the data. I just call that method, that find method, that returns the index of where something is. So find it. If index is -1, so we haven't looked at find yet, but find will return -1 if it doesn't find the thing we're looking for. That's just a special value, okay? So if index is -1, we haven't found anything, we'll throw an exception. I guess target not in list exception or something. Some value. Because again, why use an exception? Well, I don't really know what you want to do if you ask the list to remove something that doesn't exist. Do you want the program to crash? Do you want to ask the user for input again? I don't know. That's up to you. Yeah.
For these comments, are you saying that the first line of comment is what's better for Windows, but the one that's not commented out works for everything?
So the one not commented out will work for everybody. The one on top, it's not that it's better for Windows, it's just that in Visual Studio, with Visual C++, it lets you do that. And it's kind of handy because you can pass like a string along with the exception really easily. So if I get an exception, I can be like, okay, what was the error message?
Okay.
But it doesn't really matter at this stage. So if we don't find it, throw an exception. Otherwise, get the element at index, shift down to index, reduce size, return the element. This bottom part here is the same as remove first, except instead of 0, we replace it with the index that the thing is in. Any questions? Yes?
So this is an ArrayList implementation. So let's say you're removing something from the middle of the list, right?
Yep.
And just so I'm clear, you can't physically actually remove something entirely from a list. It's always going to be allocated, right? Like the memory will always be allocated to that thing that you're trying to remove, right?
I'm not clear on what you're asking.
So basically, all I'm trying to say is when you take the thing that you want to remove out, like when you assign it to T element, right?
Yeah.
Does that thing physically leave the list, or do you just overwrite it? Is what I'm
The thing, well, it's going to get overridden. So in the shift down. Shift down will then overwrite it, and then it's gone. It's not in that list anymore, in the array.
Because the premise of the question is just kind of like, does it actually ever physically get taken out of the list, or is it still kind of there until it gets overwritten by something else?
I suppose between the line T element equals list and shift down, it's still in there, but like that shift down will immediately overwrite it so that it ceases to exist. I see the nuance of your question. So the answer is yes, it still will exist. I could have written list at index 0 be 0 as a temporary nothing, but it's kind of overkill because shift down will immediately overwrite it.
Yeah.
Other questions? Okay. First, well, okay, return that. Last, return size -1. Cool. Contains, well, just do the find, and if the index is not -1, I found it. If it is -1, that's the special value that find will return if it doesn't exist. Size, return the size. Is empty, is size 0. Cool. Did we actually look at find? I guess we did look at find. Yeah. So if it doesn't find it, we return -1. That's all. Any questions about this high level list? Was that an ordered list? Was it an unordered list? Was it an index list? It was just a list. I know why you thought, well, it's got an array, you can index. Well, as far as the list is concerned, it's not. So, that's our general list. That's our base class. It's kind of useless. There's no way to actually add anything to this list. It's so simple, it can't do anything basic. Before we move on to ordered list, any last questions about lists in general? Okay, we're all good. Okay. So, I guess now I'm going to make the ordered list. It's going to inherit from ArrayList. It's going to be generic. It's got nothing new to add in terms of the private. It's got our constructors. And I'm probably just going to pass that constructor on to the original base class's constructor. Although we'll see. Maybe I'm wrong. But the only thing new here is add. That's the only thing I actually want to add to the subclass. Array ordered list, the only really new thing is the fact that I'm going to add something, and we're going to specify the rules on how to add. Okay, so, array ordered list, there's nothing there. What is this doing? When you look at this code, what does this mean to you?
It is calling the parent.
Bingo. It's just calling the parent class. That colon array list T, that just means like, just pass the buck. Same with down here. Same with there. We'll automatically call the base class constructor. Cool. Deconstructor, pardon me. So I didn't even need to add anything new here. And here's our add. Now, in our current situation, we do need the this to be able to access the protected things from the base class. So the this, remember, that's like a pointer to me. But look at this code. Take a second. I don't want to explain it. I want you to figure it out. Nothing in here should shock you. But look at it piece by piece. What's it doing? I'll give you 30 seconds. So let's break this down. What does the first bit do? Those 1, 2, 3, 4 lines of code, including the squigglies. Just, if I'm out of room, I gotta expand capacity. Cool. Then the expand capacity, well, we just get to call the parents class's expand capacity, which is awesome. Then what? Well, the next 1, 2, 3, 4, 5 lines of code, what's that doing?
Changing the position.
Increasing the index until we find a number that's greater than the L.
Exactly. And even more simply put, it just goes and finds the index where the thing would belong. And how are we doing that? Well, based on what you're saying. Well, the index is less than this size. By the way, I could have done this with a for loop. It's fine. I just used a while loop here. Start index at 0. Well, the index is less than the size. Okay, well, there's still room to go. And the index, the thing at the current index is less than element. Keep going. Is that right?
Yes.
Right. Yeah.
So this is like, we're using generics for this, right? But this would technically only work with like floats or doubles, right?
This technically would only work for things that, I want to point out that the question you just asked is amazing. Look at this. 2 classes in a row, you asked a brilliant question. I'm going to ask his question again to the whole class. Or his comment. Well, this will only work for things like integers and floats and whatnot. And I know why you're asking that question, because less than, and equal to, and greater than, all those types of operators, they're defined for those things. But the response to your question is, this will only work for things where less than, I guess here, is defined. What does it mean for something of this type to be less than this thing of the same type? So, fantastic question. This assumes that we can compare the things of type t. If t was an integer, we're good to go. If t was a car part, well, let's hope someone defined what it meant for one car part to be less than another car part. If they didn't, this won't work. Because C++ will say undefined operator less than for things of type car part. But by the way, and I think we have a class on it, I'll show you how you can actually define what it means to call less than on whatever types you want. I think we'll see that in class, later on in the semester. If not, not that big of a deal. But yeah, this assumes that we can actually compare those things. So this goes back to my rant last class about, well, what does it mean for this marker to be less than that marker? Well, computer doesn't know. You're going to have to tell them. Yeah?
Just a question. Let's say the element was like a string. Would C++ be smart enough to maybe default to taking the ASCII values of each character inside that string and then maybe comparing that number from each ASCII value?
So it's not that C++ is smart enough. It's that was less than defined for a string. And in other languages I know it is, and it does something about these ASCII values and whatnot. I'm not 100% sure, right? I'd have to go look at the definition of that less than. But I assume C++ would as well. But does that make sense for what you want? Do you want it to be alphabetically? Do you want it to be length of the string? Do you want it to be?
Well, yeah, like a default.
Yeah, sure, yeah. So I'm pretty sure there is one in C++. I know in Java you can do it. Pretty sure. I think you can in Python too, but I'm not 100% clear on how it's defined. Other questions or comments? By the way, amazing question. Good job. You should feel really good about yourself. Yeah?
Well, it just occurred to me that you wouldn't, why would a user ever use an ordered list with things you couldn't compare order of? So
That's true. That's true. What would be the point of it? But there's nothing stopping me from creating an ordered list of type car parts. And then when I go to add it, it might not make logical sense for me to do it, but I can do it. But now we'll have undefined, questions. It's going to be okay, think about it mathematically. Is this car part less than another car part? Well, what if that doesn't even make sense? So we'll have this undefined behavior that we want to use, but it's not defined, so we can't. It doesn't know how to do the operation. Yeah?
Wouldn't it be better then to just to choose the design option of just throwing an exception if it's not something that can be ordered, categorically ordered? But
Maybe that's what we should have done. Maybe a better implementation of this would say try to do this, but if you can't because there's no such thing as a comparison between these two objects of this type, then we'll throw an exception saying no, you can't, sorry.
because we could run into problems later on down the line where you could have an infinite amount of different comparisons. Because comparing something, especially car parts, it could be completely subjective. One person could think.
Right.
So,
Yep. Absolutely. Any other comments or thoughts? Yeah.
In the previous slide, we have this constructor, copy constructor, and deconstructor where we are defining nothing specific for array ordered list. So is it mandatory to declare them for specifically for
So we do have to redefine them for array ordered list, but we're being really lazy here because it's going to be exactly the same as the other, so we just pass the buck.
So we have to define this.
We do, yeah. Yeah.
So why didn't we have to, for the deconstructor, have the parent class called with it?
Oh, because it will automatically call the base class deconstructor. That's also one of the consequences of having virtual there. Don't worry too much. Okay, let's move on. So that's it. That's it. Everything else we need came from the base class. We're good to go. So let's have an array unordered list. So it's basically the same, but now we have add to front, add to rear, add after. But we don't have the add from ordered list. Because what's the parent class of unordered list? ArrayList. What's the parent class of array unordered list? We have array unordered list, our array list, then we have ordered array ordered list, and then over here we have array unordered list. This isn't below it or anything. They're like siblings in the hierarchy. So we still are pulling from here. So the fact that add was defined over here has no effect on this. Independent. Add to front, add to rear, add after. So there we go, there we go, there we go. Add to front. Well, if we have to expand capacity, we're going to have to expand capacity. That's going to happen. Otherwise, shift everything up starting at location 0. Basically make the 0th index free. So shift everything up. Add the thing at location 0 and increase size. That's it. Add to rear, that's even easier. We don't have to shift because it's the next available spot. Assuming we don't have to expand capacity, but we've got that in there. What's the computational complexity of adding to front? N, 1, n squared, getting them all.
Expand capacity.
Exponential?
No.
Oh.
If expand capacity is there.
So if we have to expand capacity, it's definitely n. But what's the complexity of shift up? N. We have to shift up. It's going to be n no matter what. So we need to make room for it. What's the complexity of add to rear? 1, or if we have to expand capacity, okay, we'll think about that amortization. But really, it's just 1. Add after. Okay, go to find it. If I don't find it, we'll throw the exception. Add after a specific element. Well, if that thing isn't in there that I want to add the new thing after, well, I can't very well do that, can I? Add after Bob. Are you Bob? 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 Well, I can't add it then, right? That's a silly question. So that's what the exception's doing basically. Go find where Bob is. Oh, Bob doesn't exist. Okay. Well, let's say Bob does exist. Okay. Well, if I have to expand capacity, and then I have to shift up from index plus 1. Why index plus 1? Bingo. Because I found Bob at index, and I wanted to add it after Bob, which is index plus 1. So everyone has to shuffle down over there. And now there's room to add them and then increase size. Any questions? What's the computational complexity of this one? Why?
Just doing like one linear search.
Well, we have to do find. And find takes how long? N.
N.
We might have to expand capacity. How long might that take? What about shifting up? How long does that take?
Index.
N. I mean, we might get lucky and index might be at like the end. But we might also get very unlucky and index might be like 0 or something. Or I guess it can't be 0. It would have to be at least 1. Can't be 0 because if we're adding after, yeah. Point being, this is order n. So like ordered list, that's it. Nothing extra fancy here. Again, everything else we needed came from the base class. We got lucky. So now, array index list. So now, we're getting a little crazier. We're adding a lot more interesting things, I guess. We've got, I guess, nothing private, but we've got our constructors. We've got 2 adds. Add at a given index, and add, I guess, after something. set something at a given index to a value, get something at a given index, find the index of a specific element, assuming it exists, remove something, and then what's this thing here? Does that look like something we've seen before? You might be right, I don't know, we'll see. Does that look new? Everybody say yes. Yeah, but we'll see that in a moment. And you know what? Let's end here just because I don't want to get halfway through this. Alright, I'll see you tomorrow.